I wanted to work through a problem that involves stress, strain, elasticity. In this problem, we're imagining that we've constructed a cable out of two wires, one wire connected to the other wire. The two wires have the same lengths and the two wires have the same cross sections, but the two wires have different materials. Maybe they're aluminum and copper, or brass and steel. And we want to figure out an equation or a formula for the elasticity or Young's modulus of this cable that's made of the two wires in terms of the elasticities or the Young's moduli of the two wires themselves, of the brass and the steel, or the copper and the aluminium. So let me start by making a sketch of the arrangement. And I'm going to imagine I got one wire here in blue. It's hanging from a support. And then the second wire is connected to the first wire. Here it is in red. And maybe we're hanging a mass from this arrangement of the two wires. Now, what we're told is that the two wires have the same lengths. The two wires have the same areas, cross-sectional areas. But the two wires are different materials, so they have different elasticities or different Young's moduli. And so I've indicated that here. So the lengths of the two wires in L, the cross-sectional areas are this uppercase A, the elasticities are the Y1 and Y2. Now, this cable that's made of these wires, like the individual wires themselves, will stretch when we apply a force to the cable. And the effective Young's modulus, effective elasticity of the cable, tells us how much that cable as a whole stretches. And it will tell us that in terms of how the individual wires will stretch. And so we're going to find a formula for that effective Young's modulus of the entire cable. So we're calling that Y, and we want to calculate that. Okay, so here's where I'm going to start. I'm going to start with the basic relationship between the elasticity and the stress and the strain. That elasticity is stress over strain. Remember, stress is the thing you do to the wire. Strain is the consequence for the wire. So the stress involves applying a force to the wire. The strain reflects the elongation of the wire. And actually, we can write that out as the stress is force over area applied to the wire. The strain is the elongation divided by the length of the wire, the fractional change in length of the wire. Okay, so let me add to the picture one more quantity, and that's the elongation of the two wires in the cable. So when we apply the force to the cable, and consequently the force to the individual wires, wire number 1 is going to stretch. I'll call its elongation delta L1. Wire to number 2 is going to stretch. I'll call its elongation delta L2. And the cable itself as a whole will also stretch. And I'll call that elongation delta L. Now, an important thing is that the elongation of the entire cable will just be the sum of the elongation of the first wire, delta L1, and the elongation of the second wire, delta L2. So So however much the first wire stretches plus however much the second wire stretches, that's the total stretch of this arrangement, this cable made of those two wires. Now another important point. The weight or the mass that we hung from the cable, that is causing a force, I'll just call it F, on this lower wire. It's causing a tension in that lower wire. And that force, that tension in the lower wire, is transmitted to the higher wire. So assuming that the masses of the wires are negligible compared to the mass that we hung from the wires and caused the stress with, the force that causes the stress on the first wire and the force that causes the stress on the second wire are the same forces. So that's a second important point, that the force on the first wire and the force on the second wire, maybe I'll write them as F1 and F2 on the picture, are the same force. They're just transmitted through this cable. Okay, so those are key ingredients. Now what I'm going to do to actually solve for the Young's modulus of the cable in terms of the Young's moduli of the individual wires, I'm going to take this first equation here and I'm going to write the elongations. I'm going to write them in terms of the forces, the areas, the lengths of the wire, and the Young's moduli of the wires. So let me show you how I'm going to do this. So delta L1, if I rearrange this master equation upstairs here, delta L1, the elongation of wire 1, will be the force acting on it, its cross-sectional area, divided by Young's modulus of wire 1 over the length of wire 1. Likewise, the elongation of wire 2, that will be the force on wire 2 divided by the area, cross-sectional area of wire 2, and that's divided by, rearranging this equation, the Young's modulus of wire 2 over the length of wire 2. And those will be related, the sum of those, the total elongation, will be related to the effective Young's modulus, which is on the cable, in terms of the force on the cable, the cross-sectional area of the cable, the effective Young's modulus of the cable, divided by the length of the cable. And that's 2L. So the two wires have length L, notice. The cable has length 2L. Well, now if I rearrange this equation by canceling out things that are common to every term on the equation. So, for example, the forces will cancel one another out. Every term has the force in it. And it's the same force applied to the cable that's applied to the individual wires. Every term has the cross-sectional area in it. It's the same cross-sectional area of the individual wires in the cable. Every term has a common L in it. The lengths of the wires were L, and the length of the cable is 2L. And so the F's, A's, and L's all cancel out, and you've actually got the following equation. That relates the effective Young's modulus of the cable, that's the Y without the subscript, to the individual Young's moduli of the two wires that made up the cable. And so that's the answer to this problem. It's an equation that tells you if you combine together two wires of equal length and equal cross-section in what we call series, connected end to end, then the effective Young's modulus of that cable that you've made out of these two wires is related to the individual Young's moduli of the two wires, of the two materials in this particular way. And so that's the answer to this question. Now you can look at this equation, you can ask the equation a few questions. I mean, you can ask yourself a few questions about the equation. And one question I might ask myself is, what happens if the two wires are actually the same material? So if the two wires are the same material, y1 and y2 are the same, i.e. y1, say, equals y2. In that case, you've got 2y over here on the left. That's the effective Young's modulus. And you're going to have 1 over y plus 1 over y, which is 2y on the right. And so if the cable is made out of two wires, the same wires, the Young's modulus of the cable is the same as the Young's modulus of either of the wires, which obviously makes sense because you've just made one wire out of the two wires of the same material. Another extreme would be, supposing you made a cable that was made of one material that had a small Young's modulus and one material that had a large Young's modulus. So that might be, supposing for some reason, I make a cable out of a nylon wire, small Young's modulus, and a steel wire. It's a very high Young's modulus. So if you do that, what you find is, if you use this equation, right? So supposing the steel wire was wire number 1. Its Young's modulus is very large, so this first term will be very small. Second wire is the nylon wire. Its Young's modulus is small, so the second term is much larger. You find, because of that, that the Young's modulus of the cable, the effective modulus of the cable, is entirely determined by the effective modulus of the nylon, the effective modulus of the easier to stretch, more elastic wire. And so if you make a cable out of two wires, and one of them's easy to stretch and one of them's hard to stretch, one of them's elastic and one of them's rigid, then the Young's modulus of the entire arrangement will be determined by the Young's modulus of the easy to stretch, the very elastic wire. And that makes sense too, right? If you made this wire out of nylon and steel, well, the nylon bit would stretch a lot. The steel bit would barely stretch. And so it's the nylon that's determining the effective Young's modulus.